Again, you need to be quiet. All right. Chlorine. Chlorine. Hey, Bear Man. Sick? Earbuds, guys, earbuds. Hey, Bear Man. Sick.
Okay.
You cannot connect if you're not using earbuds, because what's going to happen is I'm going to pick up your audio and then rebroadcast it. It's going to get all crazy. Yeah, so it sounds better. People are listening. Good. I want to give it a couple more minutes, and I'm just going to start talking a little bit. Someone in the class can connect to me with questions, but we are currently going to be working on that worksheet that you should be printing. Yeah, I'm hearing my voice. Okay, so what I'm going to do is I'm going to share my screen, and I'm going to kind of walk you through the chloride worksheet that you should have in front of you. And if you've got earbuds, great. If you don't, you know, you can just watch. So I'm going to share my screen. Hopefully this works. You may not need it, and it might be helpful just to do it yourself and look at the key. But we're using our new tools, which is using formal charges to evaluate our structures, and it helps us with these more advanced structures. Okay, so in any case, I'm going to continue on with our sheet here, and let me share my screen, although I do have, sounds like an email, so let me just check that. Alrighty, I'm dropping this down here. Okay, so let me bring myself back up, and I'm going to share my screen, and let's go to this one. All right, you should be seeing this screen popping up. Okay, so we're in the Lewis dot diagram of the, well, if you remember what type of the ion is this, and if you remember, when you have a low number of O's, it's an ite, and the lowest one is the hypo. So this is hypochlorite ion. Any case, ClO0. So we always start out with the something that works. Here we go. We always start out with the valence electrons. Okay, so I'm going to start out with Cl, and I'm going to put out the valence electrons. And I always start out with the number given to me, which is 7. And then I've got an oxygen, and it's got its 6. Okay. And the only thing I can do in a scenario like this is make one bond. So I've got my 6 valence electrons. And so what I do is I make one bond. All right. And there it is. Now, of course, when we evaluate this, we see the chlorine has its stable octet. You know, it's beyond row 2. So it could have more than 8. But not necessarily in this case. This requires 8 because it's a row 2 element. All right. But you notice by sharing, it only feels like it has 7. So what we're going to need is we're going to need another electron from the environment. So this electron came from the environment. And because we're needing an electron to make this work, then this entire structure should be put in brackets to show that the entire structure gained 1 electron. Okay, now what we can do now is use our formal charges to figure out if in fact our structure makes sense, and it gives me a -1. So what I can do is say, okay, the chlorine here has 7 valence electrons. I subtract the assigned electrons. Now the assigned electrons are half of its bonding, so that's 1, plus all of its lone pairs. So in this case, that would be 7. And as I've been doing in my lectures, you can do this as well. So you can take this and see, okay, half of its bonding, and say all of these electrons are assigned to the chlorine. All right. All right. And we have... All right, so getting a message from the class that say you don't have this one, you don't. This one you're going to have to print. I thought I put that down, but so yeah. This worksheet should be posted. Refresh your page or something, or don't refresh because you can't hear me, but any case, just draw ClO0 negative on a piece of paper at this point, okay? And then I will post the this worksheet up. I thought I did, maybe I did it wrong. Who knows? Okay, those microorganisms are getting everyone here, I guess. Anyway, so just put this one down. All right. Any case, so I have this 7 minus 7. And of course, that's going to give me a 0 for a formal charge. So clearly the formal charge on chlorine is 0. For this to make sense, it should be -1. All right, so we'll do the same thing. We take all the valence electrons for oxygen, 6, and we minus the assigned electrons. Remember, this is just bookkeeping. It doesn't really mean this is actually happening. It's a way for us to make sense of all of this. And same thing, we take all of the lone pairs, which is the assigned, and half of its bonding. Yes, I'm including the one it had to absorb from the environment to make it work. And if you count, it looks like we have 7 assigned electrons. And you can see 6 minus 7 is going to equal that -1. So this oxygen gets a -1. The total of all of the formal charges has to equal the actual charge on the polyatomic ion. All right, so that is correctly drawn. And you need to use formal charges to help you figure out, and it's an important tool, especially when the structures start getting more complex, as they will as we go down. Now, electron domain geometry, okay, well, this is going to be linear. Molecular geometry is also linear. 2 atoms can only be linear, okay? The hybridization, well, I probably would say none in this case. And the reason I say no hybridization is I don't think I need to explain the hybridization between 2 objects. You think with me, one unhybridized P is overlapping another unhybridized P of the oxygen here. Okay? Now, some people would say, well, why don't you put double bonds in the oxygen? Well, if I put a double bond in here, the chlorine would have a total of 2, 4, 6, 8, 10. Okay. And you say, well, it can do that if it's expanded octet. Yes. Okay. And this would also have it's 8. And if we do formal charges, we can see that. So let's see that. Let's say if you did put a chlorine, okay, and we put, let's just redo the same kind of scenario here. Here's this. Here is the lone pairs. And here is the red. And let's put another a pair here by the oxygen. 1, 2, 3. And it has 3 left. And then we have a dark or a triangle to represent the electron in our structure. So we do the formal charges here. We have 7 that are assigned. Okay, a 7 valence electron minus what? Half of the assigned ones. And let's do that. So it'll be something like this. It doesn't matter whose electrons it first was, but now I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then if I did over here, I would have the assigned electrons for this guy would be, well, the 6 valence electrons minus 1, 2, 3, 4, 5, 6. If you notice, we would get a 0 for the oxygen, and we get a -1 for the chlorine. The whole thing would equal a -1. That's good. But according to what we learned, if we're going to have a negative formal charge, it's going to be on the more electronegative atom. Between oxygen and chlorine, oxygen is more electronegative. So that means that this structure is not a possibility. The best structure that we can draw with dots is this one, and I hope you can see that. This works because this is an expanded octet. This should be able to work. But in the case drawn here, that would make the chlorine more stable. Make the chlorine -1. And that -1 has to go on the more electronegative atom. Now remember, what does this really mean? This means that the chlorine is gaining an electron from the structure somehow. Somehow this chlorine is taking an electron, okay, to make it work in this structure. Okay, now there's no way that chlorine can do so if it's not as electronegative as the oxygen. It's the oxygen who would be taking, okay, to make this work. And it took from what? The environment to make it work. And of course, it makes sense the oxygen would do that if it's more electronegative. So the reason why this is the correct structure, formal charges help us. Now, the hybridization part, you should be able to figure this out. If it's just one bond, chlorine, okay, just has a what? An unhybrid orbital at the end. So it would just, I'm sorry, 1 electron here from the chlorine, and then you've got what? An oxygen, and that would just what? Overlap its unhybridized orbital. We don't need hybridization to explain the bonding here. Okay, obviously you're going to have to finish out the string here, you have your S, but you can only explain this sigma bonding. You can explain it with just unhybridization. Remember, hybridization is a theory to help us explain things we already know. We don't need it to explain here, okay? So it's not necessary. So no hybridization needed. These are 2 terminal bonds. So you can use unhybrid P's to do that. Bond angles are 180. And yes, this is polar. Actually, I'm sorry. You would say non-applicable here. Now, normally you say, well, why not? Well, if it's got a charge of -1, this is now an ion, so it's not applicable. Ionic compounds are not polar. So ions are not polar because the entire ion, this entire area, is -1. There's no poles. The whole ion is -1. Okay? So what I would try to do now is try to do number 2 now, and we'll go over that. And 2 now, if you don't have this worksheet, you're doing ClO2 negative. And this is the chlorite ion. Okay, try that. Use your formal charges, and I will check any messages we have here. All right, so I'm going to start. Why not? All right, and make some space for myself here. So this is the chloride molecule. We have our Cl. Let's put out our valence electrons. We have 7 of those blue dots. Okay, and then we have oxygen. Now we have 2 of them. So this is kind of strange. How are they going to bond? Now, I don't know. You don't know. I don't know. So we're just going to throw them in there. All right, so here's an O. And it has 6. A lot of times we have to rewrite these to make it work. And I'll have to throw an oxygen over here. I don't know if it's going to work, but I'm just going to throw in my valence electrons and move accordingly. So maybe I should move this downward. That didn't work. Let me just do this. All right, just move that back down. Oxygen. And draw in the valence electrons. Always start with the valence electrons. And I know this thing is a -1 charge, so I am going to add in an electron from the environment. Remember, to make this polyatomic work, it needed an electron that was somehow hanging out there. All right, and it grabbed it. Okay. Boy, that thing gained 1. Let's see, this oxygen feels like it has 8. This chlorine satisfies the octet rule as well. In fact, all of these satisfy the octet rule. All right, now, you may say this could be correct, and you know what? It may be, but here's where formal charges help. How do I know it's correct? Well, we're going to follow the law of formal charges. So, looking at oxygen's formal charges, very simple. Let's go find that oxygen has 6 valence electrons minus the assigned electrons, which are the lone pairs and half of its bonding. I don't care if it's red or blue here. In my drawing, oxygen needs, okay, needs this many to make this structure work. So it's kind of gaining 1 here. So in any case, it's 6 plus 1. All right, it's 7. All right, so 6 minus 7, this oxygen is -1 formal charge. That makes sense. Oxygen is electronegative. Okay, let's go on to the chlorine. Chlorine's, okay, is using half of its bonding. The rest are lone pairs. Okay, and if I look at this, I've got 7, which is the valence electrons of chlorine, all of its lone pairs, 1, 2, 3, 4, and half of its bonding. So 1, 2, 3, 4, 5, 6, 7 minus 6. Okay, and you can see that 7 minus 6 is plus 1. Okay, and the last one, and you don't have to draw these. I mean, you could actually just do what I'm doing, but in any case, you take all of its lone pairs and half of its bonding. And what do we have here, party people? We have 6 valence electrons minus 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. Okay, and 6 minus 7 is a -1. So we can see that the formal charges do help us figure out that this entire structure is -1 still, as we know. How do we know it's -1? I'm just adding the formal charges. Okay. Now you may say, well, how do I know there's not a double bond? Well, you don't. So that's what we're going to try now, because maybe we know that oxygen, when its most stable form, is when it has a double bond. We know that because oxygen likes to have a 0 formal charge. So let's try it. Let's do it again. So I'm going to write this again. Here's my oxygen. I'm going to put a pair of red here. Okay, and then fill in the other lone pairs. This is trial and error, but I do know that oxygen likes to make a double bond. So I have to consider that. Okay, then I have my chlorine. It'll have these blue ones here, and I'll put the lone pairs here. Lone pair here. 1, 2, 3, 4, 5, 6, 7. It's sharing a black triangle that came from the environment. And then we have the oxygen with its 6. And let's evaluate this, and this should be getting faster now as we understand what's going on here. 6 valence electrons, okay, half of its bonding, clearly, okay, that's 6 minus 6, and you can see why 6 minus 6 is something I consider for a double bond, because that gives me a 0 formal charge, and it's something oxygen likes. Okay, now chlorine, this would be all half of its bonding, so these two count, and then half of its bonding in lone pair. So 1, 2, 3, 4, 5, 6, 7. 7 minus 7 gives me a 0. Okay, and that's a cool thing, because as we learned from last night, when you can have the lowest formal charges, that means that there's the least amount of movement of electrons to make your structure work. And the next one, you take half of its bonding and all the lone pair, and what we get is 6 minus 7, which gives me a -1. So you can see, party people, that the best structure you can draw is a double bond with the chlorine with an oxygen. Why? Well, number one is that you get the lowest formal charges on these elements. And what that really means is, remember, formal charges are just bookkeeping. They just tell us when we draw the structure that these have the least amount of movement. Oxygen didn't used all of its electrons to make the structure work. Chlorine used all of its electrons plus 1 from the environment to make it work. Okay, now whether I put this black dot here for the oxygen, or I should say, I don't know my shapes, triangle here or here, it doesn't matter. The bottom line is chlorine is using all of its dots, or all of its structures, and I guess the best way is to have the blue dot here and this here. It would make sense that the oxygen gained that electron. So I really should have drawn it that way, but that's okay, you get the point. Okay, so this is the best structure because you have zeros. The negative is on the more electronegative atom. And what all that means is, again, when we draw the structure, it makes more sense that the most probable structure is the one where the elements are using their own electrons to make it work. All right, very simple. So this is the structure, but I'm going to redraw it because when I look at it this way, it confuses me. All right, so I look at the chlorine structure. Okay, it's got 2 lone pairs. So for me, I'm going to put the 2 lone pairs on top to help me remember that, my gosh, these are bending down. Then I have a double bond to the O. And I got a single bond to another O. And this entire structure is -1 charge. Now, can anyone out there know if I'm done? No, I'm looking very carefully here. Is this am I done here with the Lewis dot diagram? Oh, Bryce, you're so right. Okay, yeah, we have to draw another structure, okay? Because we have resonance, and resonance shows, because I have a double bond here, that double bond can be over here. So I'm going to draw another structure with an O. Make sure you have the right number of dots. That would be 6, right? A single bonded O is going to have 6, and a double bonded O now has 2. So we draw brackets, and we draw charges, and this is the Lewis dot diagram, the complete of the chlorite ion. All right. If we look at some of these questions here, the electron domain geometry, well, considering, okay, we have 1, 2, 3, 4, we would say that this shape, okay, is in a tetrahedral. So the electron domain geometry is in a tetrahedral. The molecular geometry would be just what? Yes, that's correct, Malini, bent. All right, freaky, isn't it? All right, now, being bent means that it would have a polar shape, but it's an ion. Any case, we're running out of time. So what I would like you to do, the bond angles, of course, are 109.5, and of course, not applicable, the polarity, because it's an ion. So I would like you to complete 3 and 4. All right, whatever I post for the homework. Thanks for playing today. And thanks, Sammy.